Hey, welcome back, everyone. It's been a while. I've been really struggling with these batteries, trying to get them all figured out, but I finally think I have. So now we get part two of the video we started last time. So, all right, I'll show you what I got going on here. So here's the batteries from before. Uh, I now have overcharged a second cell. I believe it's cell 8. That's the one that the probes are on right now. You can see it's up to 3.65 volts according to the meter. The first thing I did was I took this ribbon cable. It's a 10-pin ribbon cable that fit into this kind of strange connector here. But in order to get it to fit, I had to cut off that little protrusion or the clip on the right side. And so this is what started the debugging. So in order to connect to the board, you just need 5 of the 10 wires. So you got power, ground, CAN high, CAN low, and then there's like a ignition input that doesn't seem to make much difference whether that's on or not, but there is a CAN signal that indicates whether or not it's been triggered. And then the other 5 wires would be daisy chained into the next one. So I started with this kind of mess that I got here, and then later I was able to find the actual connector on Mauser. So I ordered 14 of them actually, and I made this using 2 of them here, and then I'll use the other 12 for the actual harness that'll go in the cart. So this is kind of cool. So basically this represents the ignition switch for testing. You got 5 wires going into the first one and then 5 going into the second one. Then also, because it is supposed to have a termination resistor at the end, that's what that right there is. So yeah, you can, it's pretty nice. It plugs right in. It's a really quite a good connector. I'm pretty happy with it. And then here I've got my USB to CAN from Grid Connect with a connector on it. So I'll connect this up, and then we'll go over the software, and I'll tell you what I've learned in the last 2 or 3 weeks, however long it's been. All right, here we go. This is my first video ever doing a screen capture. I'm pretty sure that I'm recording in 4K, 30 frames per second. The computer's not the fastest, so we'll see how many frames per second it actually records, but hopefully this turns out okay. Basically what I'm going to go and do here is I'm going to go through the process that I went through, obviously sped up because I've already figured this out, to get these CAN bus signals deciphered and figuring out what signals I need to send to turn on balancing for these battery packs. So here we go. I'm using SavvyCAN version 208. I believe it's the most recent version. It seems to be a pretty popular program for doing CAN bus hacking, especially in EVs, from what I've been reading online. So here we go. First, we're going to make a connection with the USB Grid Connect PCAN USB to CAN bus adapter that I have here. You can see it's listed here. This particular device uses 500 kilobits per second, so you got to set it to that, and then you save the bus setting. And you can see right away we've got some signals coming from the one pack that I have connected. When you first open this program, it's going to be more like this, where it just kind of keeps rolling in. That might be useful in some CAN buses where you just really have a ton of data. Since we're just working with one device, the overwrite mode is really nice because it just shows you the updating data on the packets that are coming in. In this box right here, you can see the different packet IDs. I've only decoded some of the data in some of these IDs, just enough for it to be useful for what I'm doing here. These shorter ones are what they call 11-bit CAN bus IDs. These are the packets that contain the voltage on the different cells. And also, this address is useful in determining these other addresses and also the balance address that you're going to send information to later in order to turn on the cell balancing. I have 12 of these battery packs. I've only tested 2 so far. So far, those 2 had a different ID right here. I have a feeling that the odds of all 12 of my batteries having different IDs is unlikely. It would be ideal, because then hopefully I can read all of the data from all the batteries on the same CAN bus. But I'll have to go through them all and check that later. Next, I've got this text editor right here. And as I said earlier, I've already done this, so I'm just going to show you this text file that's going to define some of the data that's in these packets. I got to be honest, there's a nice tool in here to set up the decoding, but I kind of bypassed that because in my searching for resources on these battery packs, I found some of these DBC files that define the packet information, and I've just been modifying it with the text editor to fit my needs this whole time. So I don't even know how to use the built-in SavvyCAN database editor for these. So I've just been doing everything here, and I've kind of been learning as I go. Basically, the useful information is in this area here. So like right here where it says 432, that's a decimal representation of this 1B0. So if I open a calculator and type in 1B0 in hexadecimal, you can see in decimal right here it's 432. That's one gripe I have about the text editing version of doing this, is that it's in decimal instead of hex. I would prefer it in hex, because that's how it's displayed over here. Now, granted, if I was going through the actual SavvyCAN editor, it probably is in hex. I couldn't even tell you. So, anyway, you can see with this particular address, it breaks it down into these 4 voltages for the cells 1 through 4. And it's pretty neat because the digital to analog, I said that wrong, the analog to digital converter that's on the microcontroller on this battery management is apparently a 12-bit converter. Normally, I would expect data to be in multiples of 8, but because the converter is 12 bits, they literally just use the 12 bits in the CAN bus packet, and then they stack them. So the interesting thing is, let's see, on this one right here, you can see the data that's rolling in. The first byte is 2 hexadecimal values for 0 to F. This byte is the CRC checksum of the rest of the packet. And then it also has a counter that basically just goes from 0 to F. I don't know why they do this, but they do this on several of these packets. I assume it's because it's kind of like a heartbeat. It's just kind of letting whatever is monitoring these signals know that it hasn't frozen, I would imagine. So, okay. Well, the interesting thing is these 2 bytes would represent 16 bits. But this number right here says the useful information for this particular field is going to start at bit 12, which would basically be in the middle of the second byte. And then also, another thing that I don't particularly like is the information is transmitted with the least significant bit first. I prefer most significant first because it's easier to look at and understand. I probably would have never figured this out on my own had I not had something to start with. So all of this information that's being decoded from the data being sent to me from the battery management controller is all least significant bit first. I don't know if that's what this plus sign means, because again, I've just been editing a file that I started with, so I'm not 100% sure about all of the specifics in this file, but I feel like I know enough to make this video, hopefully. So let's keep going here. I'm gonna import this file and show you how it can actually decode some of this data in real time. So you go to the DBC file manager and we'll load just this one right here. We'll close this window and actually I'm going to open it back up because I forgot to tick this label filters. See over here where it just shows the addresses. It doesn't have labels. When you click that, it puts some labels on stuff. They aren't very useful. I need to make them more I need to make the names a little bit more useful, but either way you can see that it puts the labels over there. I know that the ones that don't have labels are not useful for decoding. Okay, so you can see it did something different here, put the labels there. If I click on expand all rows, you can see that there's some useful data that's being displayed now. I like to press clear until it arranges it in a way that is useful for my demonstration here. So this is nice. Okay, so we've got the 4 11-bit addresses here that are transmitting the cell voltages. Because there's 4 voltages per packet, and we have a 13-cell battery, it uses this 4th packet to just do 1 cell. And again, this is the battery that I made the first half of this video with, where I overcharged cell 12 so that it was higher than the rest of the cells. Well, I've since also done that with cell 8, just so I had some references to know that the different cells that I charged were in the correct location and that I had this decoding done properly. So you can see this right here represents the frequency at which it's updating, and these are in microseconds. So 200,000 microseconds is 0.2 seconds. So each one of these are updating 5 times a second. Not all the packets are that way. You can see down here we got once every half second, once every second down here. So originally getting just the voltages decoded was pretty straightforward. The file that I first had found had 4 voltages per packet, but it also had a temperature reading above it that was not correct. So I've since removed that, and I can get I can get the battery temperature, but it's on a different packet. You can see it's down here. Each battery module has 2 temperature readings. I know that on the battery there is a temperature sensor that's mounted somewhere in the battery cells themselves that plugs into the BMS. So the fact that there's 2 temperature readings tells me there probably is a temperature sensor on the PCB itself. I haven't located it. I'm not even really sure, but you can see there's 2 readings. They're a little bit different. When I connect the second module here, you'll see that there's some variance between them. I read years ago that a cheap temperature probe has like a plus or minus 5 degrees accuracy, so you really can't. You can be pretty excited if it's within 1 or 2, because that's not always common. So moving down, you can see there's some packets here that I don't have any knowledge on what they do, really. Then I got ahead of myself here. I didn't want these particular packets to even be here yet because they're the balance control signals. But we'll move past that for now. This right here is the signal that comes back from the BMS on the battery, indicating whether or not the cells are being balanced currently. And you can see because this signal is present, it's showing on cell 8 and 12 that it is in fact turned on or enabled. And that's from the signal here. So if I go to the send custom, you can see that these different frames are present right now. I think it saves it when I close the program and reopen it, so that's why they're there. I meant to open them while I was making this video, but that's fine. Since that's there, I'll go over here to this file that I already saved. Basically, what this file is showing is if the first packet with the voltages matches one of these addresses right here, that would make that cell one of these numbers, I guess. So like this first one that we're looking at right now is 1B0, so we'll call that number 1. And again, I've only tested 2 batteries, but from the research I've done, it shows that there's 12 different possible first packet IDs. And then this address right here is the 2 addresses that you need to send the command to in order to enable the balancing. And the reason there's 2 is because unlike the data that you receive from the BMS, that's least significant bit first, this is a full byte most significant bit first command, which is great because it's easier for me to put together. It's easier for me to compute with any program that I might write. So yeah, it's the way I prefer it. So that's good news. And also, this packet that you send to it does not require a CRC packet, which is also a simpler situation. So no complaints there. That's great. But anyway, the reason you have to send 2 is because each one of these bytes represents a single cell and the command necessary to turn it on. So there's 8 bytes per packet, so that can only control 8 cells. So since we have 13 cells, the next 5 bytes in the next packet control balancing on cells 9 through 13. So since this is running, I have it sending 1 a second. You can see the update rate here is approximately once a second. And the reason it's at once a second is because I have it triggering every time it receives this byte and this byte, or this packet, I'm sorry. And that just makes the timing the same. I did find out that if you end this packet, it will stop balancing after some amount of time. I haven't timed it. I just noticed that it was off after I closed this program for a little while and opened it back up. The balancing had stopped, even though the battery self-powers itself all the time as long as there's any charge present, which being a lithium cell, there always should be. But anyway, I'll show you how if you manipulate this 13th byte in packet 2, make it an 8 as well, and keep your eye over here on where it says balance cell 13 is a 0. If I press enter, it turns into a 1 because it's now enabled. Now the capacity of each one of these cells is pretty significant, and I haven't checked to see what the discharge resistance is when this is enabled, but it's not significant. There's barely any noticeable heat generated on the board, and holy cow, it balances slow. I've had this balancing for, I don't know, we'll say 30 hours, maybe more, and it's gone down just a few hundredths of a volt. But in the BMS's defense, I don't know that it is likely that it would ever be this far out of whack from the other cells. That was the scenario that I created, obviously on my own, in hopes that it would self-balance without the need for me to do all this stuff. But whatever, that's fine. It makes me feel more connected, I guess, to this project. But it's really crazy that the microcontrollers are on this BMS are really quite capable, but literally all they do is check the voltage and temperature and send the data back. You have to have another controller of sorts to look at this information, make decisions, and tell it to balance. It doesn't do it on its own. there might be some consortium in the automotive market that said that's the way you should do it for safety. I don't know. It just seems like a lot of horsepower in those microcontrollers that are really going to waste in this scenario. But anyway, I'll set this back to 0 on that 13th cell. And you'll see it went to 0. I'm hesitating right now because I'm double checking my mind to see if I remember to start the recording. I'm going to stop it for a second just to make sure I did. Good news. I did start it. And I didn't just waste 10 minutes of my life talking to myself in my garage. Okay, that's good. All right. So another thing that I noticed when I was messing around with these variables is it doesn't have to be an 8. Like we'll do, this is going to be cell 9. You can see here, cell 9 is a 0. I'm going to make it a 1 instead of an 8. And you can see it's still turned on. I don't know why the source that I got this information from said to use an 8, but it can literally be anything that's not a 0, and it'll turn on. I don't know if maybe that has something to do with how it might balance. I don't know. Not sure. But okay, so that shows you how you can send this balance command. That was a big deal figuring that out. I actually thought about making, instead of a part 2 of this 2-part section on these videos, thought about making a part 1.5 out of 2 instead of 2 of 2, because I was pretty happy with the progress I made reading the values from the battery, but I was stuck. I couldn't turn on the balancing, but I made a breakthrough last minute talking with a fella on GitHub that helped me out a little bit and brought me to where I am now. So I feel like this will be a complete 2 of 2 for this video. So, all right. Now what I'm going to do is I'm going to plug in the second cell, and you can do this live. And you can see on the right, you'll see a bunch of new addresses pop in here. So they're all very similar addresses to the first one, but they aren't labeled because we've only loaded the database that I created for battery 1. And another thing, while we have this file here open, is you'll see these unlabeled ones. You see the first one starts with an IC4. And you'll see over here, IC4 is right here, and that's 6. So even though I only have 2 batteries connected, it didn't automatically assign the address to the second one here. It's like hard-coded into the microcontroller. I don't know if there's a way to change that. That's why I'm not expecting all 12 of my cells to be different addresses. I hope they are. One thing I want to point out before we proceed is this 12th cell, the address that it says to use to program the balancing is actually, it would be this one right here, is the same address that's being sent from 1B0 right here, 420 and 421. So I expect a conflict there. I don't know how that's going to work. Again, I haven't tested this far. This is data that I got off from another open source project on GitHub. So we'll just have to go through and figure that out. And later in this video, I'm gonna quickly go through my other batteries, figure out what addresses they are, and I'm going to label the batteries themselves so that when I go to install them, I will put them in some kind of order so that it'll make troubleshooting in the future. If one of them ever has a problem, I'll be able to locate them. So there's that. So now what I'm going to do is I'm going to load the database for the second battery so you can see these values right here actually get populated like the others. So I just got to go back to this DBC file manager again and load the second battery that I created. And you can see now there's values in here. So this is CMC01 is battery 1. CMC02 is the second one. Now, it's not labeled right because it should be number 6, but I didn't know it was number 6 when I started this process. So eventually I'll go through and rename everything, and I'll also change it from CMC to something that makes sense to me, and then these end labels will be something more intuitive. So yeah, that's basically that. If I wanted to control balancing on this cell, you can see the balancing is all zeros. You would have to go to send frames and change these IDs to these IDs right here. And that would allow me to control that one. So once I get the addresses figured out for all the batteries, I should know the address to send the balancing commands. And knowing all that, I basically have the batteries whipped from a using them standpoint. I still have the battery chargers and a master controller to tell it when to charge when it needs to balance, to monitor the chargers that I have kind of in mind. We'll go over that later. So that's going to do it for this. Hopefully that was useful for some people. As always, like and subscribe. That would be great. Thank you.